Great. Yeah, I'm Will. I work for Fractile. This is about Constrainedrandom, which is a Python package for constrained randomization problems. So more of the same. Bit of background. So when you create stimulus to verify a design, you rarely want it to be completely random. Designs are rarely designed to handle any input stimulus at all. For example, this design is a toy design. Says that it just doesn't work if the sum of the three values are greater than 7. Bit of a rubbish design, but there you go. So you want to be able to create random stimulus within a set of constraints, and you want the distribution of that random stimulus to be even between all the valid solutions. So I didn't realize quite how much detail the previous talk would go into this, but so you can do randomization with what we've just seen with constraints in SV, and commercial EDA simulators obviously pour a lot of money into developing their constraint solvers. So we do have Verilator that can handle System Verilog and its constraints, but what if you don't want to use System Verilog to create your stimulus? What if you use CocoaTB, or like us, you use a combo of CocoaTB online stimulus and some offline stimulus generation, like a tool that completely separately from your test bench generates transactions for you to run on your bench. For that, you might want to use something different. So the kind of standard approach would be to just use procedural randomization. So all sorts of programming languages have some kind of random, like Mercer and Twister style random number generator. So Python, you've got the random package, so you can seed that. And then here, this algorithm just simply gives you a random value between 0 and 7 for A, then constrains B not to overflow, and then constrains C not to overflow. This is correct in the sense that it will never give you a wrong answer, and it's cheap because it does the minimum number of randomizations. However, when you run it, you've over-constrained C. Because you've made it go last, it's now extremely improbable for C to ever take on large values, so you've completely ruined your chances of it being an even distribution with that algorithm. So you could spend a while thinking about that, like how would I generate a properly even statistical distribution? Or you could take a different approach. You could do it in the declarative style. So Constrainedrandom enables that. So you get this primary user-facing class called a randobj. So you can add random variables to that random object. You can add them with the correct range as their domain as well. You add a constraint, which is just a pure Python function. It returns true if the constraint is satisfied, false if the constraint is not satisfied. You can put anything you want in there. You add the constraint to the problem, to the correct variables, and then you hit randomize and you get a result. And when we run that, you see that we get a much more even distribution of the possible values. And I think I would argue that the code for that is easier to read and write. It's clearer what the intention of the code was than this version. So the goals of the library, I wrote this a couple of years ago. When I set out, I wanted to make it easy for those from System Verilog to kind of transition to use this. I wanted it to be repeatable, so as was being discussed before, the idea of seeding needed to be firmly in place. And it needed to be fast, or rather as fast as possible as a Python package could be. So we initially picked up some work that was using PyVSC, and that was unfortunately too slow for our use case. So I aimed for a 10x speed up over PyVSC. I'll quickly whiz through the features. You can read the code in slides later. So randobj, the class can be either extended from or just instanced and used. On the right-hand side is it being extended from. In that case, you can apply any kind of normal object-oriented patterns that you'd expect to be able to apply. So there's two different ways of seeding. You can either globally seed, so it uses the Python random package under the hood. So if you just seed the global package, then you'll get determinism as long as you are addressing the same problem, so that either in one program or multiple runs of the same program, the seed will give you deterministic results. But it also supports instance-based seeding, so if you have an object and you want to create a random number generator and pass it into that object, then it will use that random number generator rather than the global package. So you could have two separate instances. As long as it's the same randomization problem, those two separate instances will give deterministic results within the same run. So when you add a random variable, you do have to tell the problem what the possible values are. So the first way to do that is simply to say how many bits the variable has. The second way is to provide a domain. So a domain could be any kind of iterable, really. So it could be a range, it could be just odd numbers, it could be a specific list of things like prime numbers, it could be that enum that I've got on the right-hand side, and then I support distributions, weighted distributions via dictionaries. So with a dictionary, the value, it's a bit confusing. The keys are the values are the distribution, if that makes sense. So on the right-hand side, you've got 50% chance of getting 0, 25% chance of 1, and then 25% chance of 2 to 9. And then the third way, you can specify your own function. So for a particular call to randomize, you might want to just run a function to set the value of a given variable. That function could either be a randomizable function, or it could be a deterministic function. So you could, the time function from Python just gives you the current time in epoch time, and or you can do something a bit cleverer. You can add constraints to single variables, so you can add them as they're constructed. So there's clear utility doing this here. So you've got a nice, clean, range-based kind of distribution. You don't want to pollute that by having to artificially chop the range up around the illegal addresses of dead beef and cafe food. So you just add a constraint to say you can't do those two values. If you add the constraint as the variable's being constructed, then it optimizes as well. So it won't run that every time. It will just remove those from the possible domain. And then you can add multivariable constraints, which can be arbitrarily applied across all the variables in the problem, a subset of variables, however you want to construct it, really. There are loads of other features which I don't have time to go through in detail. So we've got randomly sized lists and random lists or randomly sized random lists. Fixed values, temporary constraints, pre-randomize, post-randomize, bunch of other stuff. You can read about that later. So one slide on how it works. So this is different to the approach that was just described. So the first approach is that there's a very naive solver which simply randomizes the variables and checks the constraints. It has a few goes at that, and often that is enough for what you want and provides a surprisingly even distribution. If that fails, it falls back to a sparse solver, which basically does a graph-based exploration of the state space, so attempts a kind of semi-depth first exploration and checks the constraints against a bunch of different possible values at each level of the tree, and then returns one if it finds a valid one. If that fails, then we thoroughly solve for all possible values of the CSP using PyConstraint, and then we pick a random solution. And note that that often can't be applied because the problem just simply is too big by construction. So that's when you get failures out of it. You can customize which solvers are used for a given problem as well by experiment. In terms of testing, we've got a load of test cases in the repo. Each test runs a ton of iterations on a given problem with a load of different scenarios, like exploiting those features like temporary values with using instant seeding or global copying the object. And then the tests also measure the performance so that we don't degrade that by accident. So running against PyVSC, these are the 5 benchmarks where I coded them up in both Constrainedrandom and PyVSC. The first 2 are very simple, and the bottom 3 are things I deliberately picked that Constrainedrandom is worst at. Like these are its weak points. So tried to find the things it's slowest at. So you can see that I got a decent speed up. This is running in an x86 Docker. PyVSC doesn't work on Darwin on my MacBook, but I'd be very interested to see what other people get. You can run them, they're in the repo. I went to a conference this year, and it turned out someone had done independent analysis. Sadly, the slides are not available from this, so I have a rubbish picture. And you can see that for low values of transactions, it's actually surprisingly comparable with SVUVM, which shocked me, but it's decent. His next slide was about how you can break it really easily, so I'll go on to that later. In terms of real projects, we actually converted the whole of RISC-V from PyVSC to Constrainedrandom, which is sadly work that is lost on a company GitHub somewhere, which will never be open sourced, which I'm very sad about. But it had a lot of other applications within Imagination, and we use it in Fractal in Anger now as well. In terms of limitations, it's not constraint-based programming, so it's not the same thing as like a system Verilog feature. So if you just add a 64-bit long and say it needs to be between 0 and 10, that'll break it very, very easily, because the fallback is to thoroughly solve that problem, and PyConstraint will just go, no, that problem is too large, I can't solve for all possible values of a 64-bit int. It's really hard to test uniformity as well, so I've tested it a lot for simple problems, but for a hard problem, by definition of the hard problem, you need to know all the possible values of the hard problem and then run it at least 10 times or something, that many times, to figure out what your distribution is. And that requires a lot of compute power for large. Imagine just a problem that has two 64-bit longs in it, for example. Immediately, you're looking at a huge amount of compute cost. In terms of future of FOSS constraint solvers, so it was briefly mentioned in the previous talk, there are plenty of open source SAT solvers or SMT solvers. The tricky bit is making these actually work alongside the concept of randomization. None of them have it baked in. So there's a clever approach in the previous talk, which I'd love to chat more about, perhaps in the unconference on Sunday. What I think we would need for a proper FOSS independent solution that's not tied to a language is to implement this on top of a number of these solvers in a very fast language like C++ or Rust, and then just put loads of handles to loads of other languages on top of it, so you can break out your constrained random generation away from your system Verilog test bench, because I think they're two separate problems. And that's it.
Do you have a question?
Me again. Sorry.
Only you.
I was digging recently and saw some interesting things on using LLMs for faster approaches to SAT solving, and some interesting things mixing up LLMs and SATs. Have you dug into any of that stuff?
I've not read anything about that, but
I'll send you some papers.
Sure, thank you.
Maybe a second one.
So have you heard of like hypothesis in Python, like a property-based testing? And if so, could you elaborate on how this compares to like property-based testing?
What was the tool called, sorry?
Hypothesis.
I haven't heard of hypothesis.
Scala check, quick check, and Haskell.
No, I don't know that. Was it around 2.5 years ago?
No.
Okay, yeah.
It is now. Yeah.
Right. I need to look into it.
Okay, so the master, thank the speaker again.